Hello, everyone. My name is Professor Manuel Flores. I am located in the University, Juarez University of Durango State, on the Laboratory for Scientific Computations, which is located on the Faculty of Chemistry Science in the city of Durango, Mexico. And I'm here to present you this poster that will be part of the 2022 Congress of the Materials Research Society in Mexico, which is held in Cancun. The title of this poster is Excited States of Titanium Dioxide Small Nanocluster Co-Sensitized with two anthocyanidin variants using TD-DFT and TD-DFT. So for the sake of time, I will focus on the images in this explanation. So this is a theoretical work using DFT, using the Gaussian version 16 software package. And what we did is working with titanium dioxide in its nanocluster presentation using a 3 titanium dioxide units nanocluster here as shown in the figure 4 in letter A. And in letter B, we see a second nanocluster, which is formed by 4 titanium dioxide units. You can see here 4 titaniums surrounded by their 2 oxygens for each titanium atom. So these nanoclusters are sensitized with organic molecules, which are considered pigments or natural pigments, which can be obtained from plants. Normally, these pigments that we selected are anthocyanidins, are considered to give color to the plants. Normally, 6 of the anthocyanidins, 6 of them are considered the most used. These are listed here in the table 1. And from this table 1, we selected the first row, which is cyanidin, and the third row, which is malvidin. Because in prior work that we did in our research group, which is our research group is registered in the Public Education Secretary here in Mexico, and is UGED CA 129 nanotechnology. That's where we work in this research group, and the intention and this with these nanoclusters then is to combine these 2 different molecules in a single system. So that is defined as a co-sensitization. So the concept of co-sensitization is or has to do with using 2 or more different dyes to sensitize the semiconductor. In this case, titanium dioxide is a semiconducting oxide that will be sensitized with these organic molecules, which work as pigments. This cyanidin normally is associated with orange and red colors, malvidin in blue and red colors. So the difference between these molecules, they are very alike. See that they belong to the same family with these 2 rings, but the difference between them is in this area where there is a torsional bonding, and while cyanidin looks like a more planar geometry, this other one has a certain angle in this 3rd ring. So this angle confers different properties to the pigment when is working on the presence of sunlight. So to measure that, we have developed this figure using the molecular orbitals for each individual participant in the system that we want to form. So we have the molecular orbitals definition for cyanidin, malvidin, for 3 of the nanoclusters that we are interested for this Congress. So in particular, in this document, we are including the 3-unit and 4-unit titanium dioxide nanoclusters. The 5-unit titanium dioxide, we will report it in a second document for the sake of room to accommodate the whole data, the whole bunch of data that we want to explain here. So when we take these 2 molecules and put it to interact with the nanoclusters, we get this kind of system. Actually, it presented some difficulty to reach the convergence of our calculations using Gaussian 16, because, well, it seems like there is some complexity in working with these molecules, which are charged with, if you see, these are 2 cyanidins, each one provides one charge, one positive charge to the system. So, well, the complexity to reach equilibrium in this kind of systems, well, it has a little bit of challenge to the program. Then we replaced the second cyanidin molecule by a malvidin molecule. So we get this in figure 5, the bottom system. So we have in the center now the 3-unit titanium dioxide nanocluster surrounded by, in the left, cyanidin, and in the right, malvidin. So this is a cosensitized by 2 different molecules system. On the other hand, we have here in figure 6, the 4-unit titanium dioxide nanocluster surrounded by 2 cyanidin molecules. Here in the top and in the bottom, we have the titanium dioxide, and we replaced one of the cyanidins, it seems like here is the one in the left, by a malvidin molecule. So we have a co-sensitized system. So what we did is compare the differences between a system which has 2 cyanidins and one that has a combined a combination of 2 different dyes. So we analyzed what happened with the molecular orbitals. We produced this figure. Here we have the 2 cyanidin and the 2 cyanidin with the 3-unit titanium dioxide. Here is the first one, and the 2 cyanidin with 4-unit titanium dioxide nanocluster is the second one. The third one is the 3-unit titanium dioxide with the combination of cyanidin and malvidin. And we missed, we haven't get the fourth one is still in process for the 4-unit titanium dioxide. So I will present that later on. The same way, we got the absorption spectra to analyze how the system changed when we used the combination of molecules. And we see in red here how there is a huge change when we use the combination of the two different molecules. On the other hand, when we have 2 different nanoclusters, the 3-unit and 4-unit, we have a very similar spectra. we have almost the same peak. However, there is a slight changes, very slight changes in this spectrum. So the main difference that we have detected here is it maybe because of the difference in molecules. When we have the same molecule, the change of nanoclusters doesn't give a huge or a big change or an important change in the spectrum. So, well, we have a lot to explain from here. For example, more details about the geometries, more details about the charge, but for the sake of time, I will leave it down here. I will leave it on here, and I will continue further on. I can share information if you like. Please contact me. Remember, my name is Manuel Flores, and I am at the Juárez University of Durango State. Thank you.